Hello, welcome to day 2 of Calculus Related Rates. I am going to put it on full screen to see maybe it looks better. Again, I'll do my best not to hit the stylus too hard on the screen, but when it does, it's going to click a little bit. We're just going to have to make do. Well, let's see. So I'm going to put down a key. I got to draw it first. And today we're going to review going over taking a derivative with respect to another variable, or implicit differentiation. I'm going to change my color. So the whole idea of implicit differentiation means we always put in this extra d over dx or prime sort of idea. So when I take the derivative of 4y cubed over dx, I get 12y squared, but times another dy over dx. 5r squared is going to be 10r times dr over dx. And 2u to the negative third is going to be negative 6u to the negative 4 times du over dx. Or if you want to do it with the primes instead, I get 12y squared times y prime, 10r times r prime, or negative 6u to the negative 4 times u prime. Remember when we always add this extra prime to it. Okay, move it up. Well, that's going to lead us into our related rates. The whole idea of related rates is that we're really doing the same thing that we just did, except related rates will deal with what I call word problems, real life applications. Okay, we're going to take the d dt of something. The derivative of some expression could be any variable with respect to time. The dt in the denominator stands with respect to time. Always going to put in the extra d something over dt. So as an example, I could put in dx over dt, or I can call it x prime, which stands for the rate of change of x with respect to time. That's what the dt on this bottom means, with respect to time. So if I want to do these examples, very similar to what I did on top, 4x cubed would be 12x squared, but with the times dx over dt, 10r times dr over dt, and 24y cubed times dy over dt. If you want to use the primes instead, I'm not going to use the primes too much today. I would get 12x squared times x prime, 10r times r prime, or 24y cubed times y prime. Move this up, do these other examples. Maybe these are a little bit harder because we need to rewrite some of these. This has to be 5r to the 1/2. This has to be 6h to the negative 1/3 before I take its derivative. If I want to take this derivative with respect to time, I get negative 12x to the negative 4th dx over dt, 5 over 2 r to the -1/2 times dr over dt. And this one come out of space, so I'm going to get -2h to the -4 over 3 times dh over dt. If you want to use the primes, equals -12x -4 times x prime equals 5 over 2r to the -1/2 times r prime equals -2h to the -4/3 times h prime. So again, we are taking the derivative with respect to time, and we're always putting in this extra d over dt or prime with it. Okay, the next page. We're going to use a lot of geometry in this section. A lot of applications that have geometrical approaches. So here are a lot of formulas from geometry between area, volume, and other things. If you're unsure if there's a weird type of problem, I'll probably give you the formula inside the problem. So I wouldn't worry too hard about the formulas as much. So let's go through an example where we're going to take the derivative of the Pythagorean theorem. Okay. So what is the derivative of the Pythagorean theorem? Well, the Pythagorean theorem is a squared plus b squared equals c squared, or for my example here, x squared plus y squared is equal to z squared. Notice I call x the horizontal side, y the vertical side, and z is the diagonal or the hypotenuse. So how do we take this derivative? Well, I'm going to take the d dt of this all. And when I do, I get 2x times dx over dt plus 2y times dy over dt is equal to 2z times dz over dt. That is me taking the derivative of the Pythagorean theorem. I'm going to divide by 2, and I'm going to get x times dx over dt plus y times dy over dt is equal to z times dz over dt. And this is the derivative of the Pythagorean theorem. Notice that we have six items here. We have the length of side x. We have the rate of change of side x. We have the length of side y. We have the rate of change of side y. Length of z. And finally, the rate of change of side z. Obviously, dx over dt is the change of x over the change in time, the rate of change. You want to write this using your prime notation. X times x prime plus y times y prime is equal to z times z prime. That is the Pythagorean theorem, the derivative of the Pythagorean theorem. Okay, word problem. I give you a right triangle of sides 3, 4, 5 as noted in the picture, and the size of the triangle is changing. The horizontal side is changing at 1 inch per second. The vertical side is changing also at a rate of 1 inch per second. I want to know how the hypotenuse is changing. So what do I know? Well, let's see. I know that this is increasing. This is increasing. And let's see, what do I know? Change this color. What do I know? Let me see. This is what I know. I know side x is equal to 4, and the dx over dt is equal to 1 inch per second. My side y is equal to 3, and the rate of change of side y, the dy over dt, is also equal to 1 inch per second. And side z, the hypotenuse, is equal to 5, and the dz over dt is unknown to me. I do not know that. So if I go to my Pythagorean theorem derivative, I have x times dx over dt plus y times dy over dt is equal to z times dz over dt. There's my derivative. I know 5 out of those 6 things. I know 4 times 1, go over for x and dx dt, plus 3 times 1 is my y and dy over dt, and my z is 5, and I do not know my dz over dt. I have right now 7 equals 5 dz over dt, and when I divide out by 5, I get dz over dt is equal to 7 over 5, which is 1.4, excuse me, inches per second. You want to call that z prime instead? That is fine. But what is going on in this picture is that the hypotenuse is changing at 1.4 inches per second when the horizontal and the vertical sides are both changing at 1 inch per second. Okay, let's scroll this up. I'm going to keep this here. Okay, so how about area? Well, what is area of this triangle? The area of a triangle equals 1/2 base times height. I have to take its derivative. I think it's going to be a product rule. So I'm going to do my product rule over here to the side. Do it in black. So right now I have a equals 1/2. My base is x. My height is y. So I have 1/2 x, and that derivative is 1/2 dx over dt. That's pretty messy. One half dx over dt, and the other one is y, and that derivative is dy over dt. And when I want to take this derivative, I get dA over dt, or the rate of change of the area, is equal to, well, one crisscross is going to be 1/2 y times dx over dt, plus the other one is 1/2 x times dy over dt. And now I'm going to put in my numbers that I know. So dA over dt is equal to 1/2. My y is 3. My dx over dt is 1 plus 1/2 times 4 times 1. And I get dA over dt is equal to, when I add it all together, 3.5, and I get inches squared per second. You need to have units. The first example was hypotenuse. The units were inches per second. Hypotenuse is a length that's inches. This is the change in area. Area in this case is inches squared, and the dt is seconds. So it's inches squares per second. You need to have units when you do these type of problems. Make sure you have units. Okay, let's go back to our 3, 4, 5 right triangle, except now things have changed. We have side x is still 4, side y is still 3, side z is still 5, except the horizontal side is increasing, so dx over dt is equal to 2. And when I do dy over dt, that is equal to -1 because it is decreasing at 1 inch per second. And my dz over dt is still unknown to me. If I go back to my x times dx over dt plus y dy over dt is equal to z times dz over dt, and I fill in with what I know, I get 4 times 2 plus 3 times -1 is equal to 5 dz over dt, or 8 plus -3 is going to be 5 is equal to 5 dz over dt. And according to this problem, I'm all done. I have dz over dt is equal to 1. Again, the units are inches per second. And if you want to work with the primes instead of the dz over dt, you can call z prime equals. So in this case, even though one side is increasing and the other side is decreasing, the hypotenuse will change in the positive direction of 1 inch per second. Okay, last page. We have a snowball that is spherical and it is melting at a 3 centimeters per minute when the radius is 20. Obviously, if it's melting, its radius is decreasing. So what do we know? I know in the moment, right now, my radius is equal to 20 centimeters. My dr over dt, or the rate of change of the radius, is equal to -3 centimeters per minute. So what do we need to do? We need to take the derivative, the ddt of the volume. Volume of a sphere is 4/3 pi r cubed. Well, if I do my derivative, I get dv over dt is equal to 4/3 pi times derivative of r cubed is 3r squared times dr over dt. If I clean this up, I get dv over dt is equal to 4 pi r squared times dr over dt. Well, let's see, what do I know? Well, I know that dv over dt will equal to 4 pi times 20 squared times -3, and my final result, dv over dt will equal -4,800 pi. And let's see, my units, well, these were centimeters squared, and this was centimeters per second. Nope. Per minute. So I get cubic centimeters per minute. Please make sure for these type of problems you do include your units. You can call this v prime if you want, but it is decreasing. That's why it is negative. So this is a big giant snowball, maybe the base of a snowman, and it is 20 centimeters in radius, and it is decreasing at 3 centimeters per minute. And overall, the volume of the snowball is decreasing at 4,800 pi cubic centimeters per minute. And finally, this last example, we have a rock thrown into a pond, making circular ripples that are moving outward from the point of impact. And the circles are increasing, the radius of the circle are increasing at a rate of 3 feet per minute. So what do I know? My radius is equal to 4 and my dr over dt is equal to positive 3 feet per minute. I gotta take its derivative, d dt. So when I take its derivative, I get dc over dt is equal to, well, 2 pi r. Pi is not a variable, just 2 pi times dr over dt. And I see dc over dt equals 2 pi times 3. And overall, dc over dt is equal to 6 pi feet per minute. That means in the moment of me looking at the radius of 4 feet, the circumference of the circle is changing at 6 pi feet per minute. Okay, the second part, how is the area changing? Well, I'm going to take the d dt of this. I get dA over dt is equal to 2 pi r times dr over dt. And dA over dt is equal to 2 pi times, my radius is 4. I didn't need that for the first part. Times 3. And I get my dA over dt is equal to 24 square feet per minute. You want to use your prime instead. I'm going to say A prime equals or C prime equals. So for part B, the rate at which the area is changing in the moment is 24 square feet per minute.